Jack Rickard, EVTV. We're going to try to do another Friday show. I'm kind of winging it this week because it's a topic too boring for my compadres. And almost for me. Actually, I like messing around with these batteries. I call it our least exciting videos. It's kind of like watching paint dry or grass grow. But in truth, some of our battery videos have gotten the highest viewership of anything else. And I think it's because it's the central question about electric cars. Let's see, we'll update you a little bit. I've been out driving the Mini Cooper. We've hit 80 miles an hour on very little pedal, a lot left. That 6-speed Getrag works marvelously. Our MES DEA motor's working pretty good. I had reported that Peter Knopf was wanting to play nice. Turns out Peter was really wanting us to delete our videos. That may have mentioned him in a negative light in the past when we explained to him that we don't do that. We don't delete videos. We add a new one each week. He became incensed, reneged on the deal to pay our in-plate expenses, and he's not going to hit me or kill me. I think he said he was going to get their company lawyer to sue me. I know a lot of you are terrified of lawsuits. I go to 3 or 4 a year. It's not a big deal. It's a mess. If you want an education, go to court and hang out for a day. It's fascinating. If people knew that stuff was going on, it wouldn't be going on. However, it doesn't bother me at all. It's kind of tough to get an award for suing a customer that doesn't like your product and told everybody you knew about it. So that's not a big deal. Manzanita Micro has put out a 225 amp charger. It takes 3-phase power. It's basically 3 of their PFC 75s, but this quick charge thing is coming. And I think that it's got a little life. You know, we talked about the Acre Wade. We've done some experiments with the PFC 75. I've talked about a mother bank of batteries. If you can get the charge time down under an hour on these cells, it kind of changes the range equation, which, again, I haven't entirely bought into. We get plenty of range. But it really is all about the batteries. I actually had a interesting exchange with a gentleman who does battery testing and makes pretty graphs. In fact, they were very pretty graphs, and he was trying to make some point with me that actually didn't even make sense, but I was kind of captivated. He said that the new cells didn't go down to 3.4 volts after you charged them, and he had a beautiful graph of this. And I got drawn into a thing. I spent 6 hours testing batteries. They all worked exactly as I've described to you in the past. You take the charger off of them. Over the course of about 180 minutes, they return to their fully charged state, which is a little under 3.4 volts. 3.4 volts is what the manufacturer refers to as a float voltage. There is no, you don't really float charge lithium-ion cells, so that doesn't make a whole lot of sense. What they mean is the fully charged open terminal voltage on a lithium-ion iron phosphate cell is 3.4 volts. Always was, always has been. This is not the same with lithium cobalt, lithium manganese cells, but it is the cell voltage on a lithium iron phosphate. If you undercharge the cell a little bit, you'll typically see 3.35 to 3.38 volts, and that's what I use for a nominal voltage doing calculations. I've got some great news about the batteries. The gentleman with the graphs, as it turns out, he had actually faked the data, sells BMS systems, and after I'd done 6 hours worth of testing on the cells and collected the data, sent it to him by email, and asked him how he got his. He made some vague allusions to a very automated NIST certified system, which he doesn't know anything about. He actually, I guess, has learned to work Microsoft Excel or something. There was no battery testing. He was faking the whole thing. Why would somebody do that? It's, anyway, we actually test them roughly. And in doing the tests, today I'm going to show you exactly how we do them. I'm happy to confer with anybody that does any testing. Say, I also got a call from the guy with the Lithium battery management systems, offering me the benefit of his many years of wise experience with batteries, and he offered to get me set straight on the BMS thing. He noted that he normally gets $200 an hour for that. I don't know what kind of engineer can afford to work as a consultant for $200 an hour, but in any event, I told him if he had battery data, I'd love to look at it. If he wants to tell me all he knows, I don't have time. And that's pretty much where it's at. If you want to show something and you want to compare notes, I'm happy to do so. I will try to reproduce your results. And I'm going to show you how we're going to do this test so that you can reproduce mine. If you do any battery testing and nobody else can duplicate it, you haven't done anything as far as I'm concerned. We're just past Easter. I bring you tidings of great joy. The central issue about these electric cars are the batteries. Now, there's a whole lot of press releases being issued right now. Toyota's starting a test program for a plug-in hybrid electric vehicle. We now have battery electric vehicles, plug-in electric vehicles, plug-in hybrid electric vehicles, series hybrid electric vehicles, duplex hybrid electric vehicles. I don't know what all this stuff is. I live in kind of a simple-minded world. You have electric cars and you have gasoline cars. You could have an alcohol car or a coal-fired car. Here's how you tell the difference. If you're standing next to a gas pump putting gasoline in your car, it's not an electric car. Even if it has electric windows, electric stereo, electric heated seats, which they've had for years, it's still a gasoline car. If you plug it into the wall, and that's how you get your energy to drive it, that's an electric car, and that's what we like to talk about. Tidings of great joy. 24 months ago, I bought a bunch of cells from a company called Thundersky in China. These are 160 amp hour cells. They're 183 millimeters wide, 276 millimeters tall, and about 71 millimeters thick. 160 amp hours, your fully charged cell voltage is 3.4 volts. We went to this. This was a Sky Energy battery. This was the same company, by the way. That's why the cases are similar, but different colors. They had a little bit of a Chinese split up, and now you have two companies. Sky Energy, January 1st, 2010, $567 million investment by the China Missile Aviation Academy. The government in China is subsidizing the development of lithium-ion battery cells. That's why we're buying Chinese batteries, and all the American battery companies are trying to sell them to General Motors instead of individuals. Meanwhile, General Motors is buying them from Korea. So it's chaos in battery land, except for these companies. And I really like these large format prismatic lithium iron phosphate batteries. These, instead of being 160 amp hours per cell, are 180 amp hours per cell. Thundersky has recently released, and we have obtained a couple for test purposes. Testing went well enough, I just ordered 40 more of them. Of the TS-LFP 200 amp hour battery. Now here's the trick. The TS-LFP 200 AHA battery cell is precisely a 183 millimeters across, 182, 276 millimeters tall, and 100 millimeters thick instead of 71. Except they're making some in the old cases at the 71 millimeter thickness, and they call them the TS LFP 200 AHA cell. You remember the AC50-02-1 motor and the variant that had the aux tail, which we denote as the AC50-002-1? The TS LFP 200 AHA cell is 100 millimeters thick, while the TS LFP 200 AHA cell, same part number, is 71 millimeters thick. Why is this good news? If you know to ask, and EV Components carries these secretly, you have to know to ask. These three cells are the same weight and the same physical size. This is a 160 amp hour cell, 180 amp hour cell, 200 amp hour cell. We're actually going to change from the Sky Energy 180s to the Thundersky 200s in the Speedster Part Duh and get an additional 12.5%, I suppose, range by changing the cell. These cost us about, $240 with shipping to get these Thunderskys. 8 or 9 months later, these were about $240, $241 with shipping. $220 plus shipping, about $240 for the 180s. Guess how much the 200s are now? If you specify the right number, and that is, let me repeat, TS LFP 200 AHA, about 240 bucks. So the cells have been the same price, they're the same size, and they're the same weight. But we've gone up 25%, 40 amp hours in the cells in that period of time from basically the same chemistry and essentially the same manufacturer. Blue Sky is now, as of January 1st, 2010, the China Aviation Lithium Battery Company, and they've gotten a big infusion from the Chinese government. Thundersky also has gotten money from the Chinese government, and this new cell adds a little bit of yttrium to the cathode material on the cell, which makes it a little bit more flexible. It gives it a little better spec sheet. Some things have changed. These spec sheets are hard on me because they have numbers that vary from sheet to sheet without any rhyme or reason or change in the model number. Instead of 4.25 volt charge, constant current charge curve, this new one is 4.0 volts instead of a 2.5 volt cutoff. And understand what that means. That is at the constant standard discharge current. Let me see what that is. Self-discharge, standard charge discharge current, 0.5 C. It would be 2.8 volts instead of 2.5 now. It sounds like, I don't know if there's a change in the cell or they're just working my side of the street and charging them a little bit lower and stopping before you discharge them as much. It's tough to tell. The constant current is still 3C. And we're going to talk about that here in a minute because I'm seeing some very strange things online about this. The impulse current now, instead of 10C, they're saying you can do 20C. Let's talk about C. C is capacity, is what it stands for. Unlike the lead-acid batteries with a 20-hour rate, the lithium ions have pretty much abandoned that, which was sort of a nonsense thing based on the Puchert effect. What this means is a 200 amp hour cell, if I took 200 amps out of it for 1 hour, that would essentially empty the cell. And 1C, 1 times capacity, would be the 200 amp hour rate. By the way, we're going to do that today. So 0.5C would be at a 100 amp hour rate. 100 amp hour rate, when these cells get 2.8 volts, you're done. That's essentially the cutoff. Most interesting is the cycle life. They're saying now, before this was a cycle life of 2,000 cycles to 80% depth of discharge. That's now up to 3,000 cycles. To 70% discharge, it used to be 3,000 cycles. Now it's 5,000 cycles. That is a dramatic increase in the life of the cell. Operating temperature, they write these numbers down, I never know. Minus 45C to 85C positive. And that's a pretty wide range. Weight, 7.3 kilograms, about what they always were. The addition of yttrium to the cathode material appears to have had a beneficial effect. Now, what would I know about that? Nothing. Let me just make up some stuff. One of the problems you have when you work on batteries is getting your wristwatch across the terminals and burning your arm off. But one of the other problems that you have with these lithium-ion cells is the lithium ions. The whole process is based on what they refer to as intercalation and interdecalation of lithium ions into an olivine crystalline structure. I'm going to talk about the anode because it's a little simpler. If you take one lithium atom and you combine it with 2 carbon atoms, it rearranges the crystalline structure of the carbon crystal. And it releases 2 electrons, which are then free electrons and provide electrical power. That's intercalation. If you reverse that process, it would be interdecalation. Decalation. Each time you do that, it stresses that crystalline structure. You're changing from one crystalline form to another, and it stresses it. After a certain number of these, you start to break down the crystalline material, and that's the life of your cell. Apparently, the addition of yttrium in the cathode side, think of it as being somewhat more flexible. It's not as brittle, and so it can take more of these intercalations and interdecalations, extending the life of the cell. So the good news is we're making progress, and part of this is kind of mechanical. How do you go from a 160 amp hour cell to a 200 amp hour cell in the same package? Here's one. This is kind of mechanical. This is a anode sheet from a 100 amp hour cell. It's a piece of copper foil, and it has a black coating of carbon and graphite on it, and that is the anode. If you slightly increased the density of the carbon, you've increased the capacity of the cell. It's just a little thicker plating on it. It's a mechanical process. It's about manufacturing, being able to achieve consistency of the thickness of that material, good adherence to the copper. There's no magic sauce here. It's not a huge change in battery chemistry or anything. They've gotten to be a little better at packaging it. Use a little thinner foil. Again, the foil is not the anode. It's a current collector. The cathode is the black stuff, or the anode is the black stuff. Actually, it's black on the cathode side. That's on an aluminum sheet. If you went to a little thinner aluminum, a little thicker paste, you've increased the capacity of the cell. So they're a little better at manufacturing them. Slight chemical change to the cell. We get 200 amp hours where we had 160. So that's kind of the The good news, we've ordered 40 of the TS LFP 200 AHA cells. And talk to David Coy at EV Components and get the right size one. If you get the 100 millimeters expecting the 71s, things aren't going to fit. And they're selling 2 different size cells for the same thing. They really don't advertise these because they can sell all of them they can make right now. That's what I'm hearing. Because of their quantity, EV Components has kind of got an inside track. If we don't blow the cover, we can get these through EV Components, and they'll be fine. It's kind of a bargain. Slightly smaller size, same capacity. If you're doing a boat or something, get the bigger one. It's probably got thicker foils. But for a car, this is going to give you more range. We talked about faking data and battery data and so forth. I've been seeing some things online that these cells can't do, 3C for example. Let's talk about sizing your pack for your car. This is kind of a function of your configuration, and it has to do with your controller, your motor, and so forth. The Mini Cooper, we're charging to 392 or 394 volts. We've got nominally a 372 volt pack. If I did 100 amps out of that, that's 37 kilowatts. If I do 100 amps out of a 100 volt pack, that's 10 kilowatts. So we're going to do a lot higher currents out of a Speedster Part Duh, 550 amps or so, than we are out of a Mini Cooper, which is a much heavier vehicle and needs a whole lot more power. But there we're taking out 100 or 150 amps. What's all this about? Well, that is the relationship. Power is basically kVA, or kilovolt amps, is the easiest way to calculate power in an electric car. And it's your voltage times your amperage. Higher voltage, you can use a lower amperage. Lower voltage, you need a higher amperage. When they say these cells can do 3C continuous, they're talking about a continuous output for maybe 30 seconds that it can put out a continuous. The pulse power is almost meaningless on these cells. It's a few seconds that it can do 20 times the C rating. So these could do 4,000 amps for a second, but they can really do about 600 amps for 30 seconds. And that's the level of current that we would need in the Speedster, and that's why we're using these cells. In the Mini Cooper, we're not doing as much. So we have 100 amp hour cells, 3 times the 100 amp hours is 300 amps, and that's the limit of our controller in that car. So you kind of have to size to your vehicle and the voltage you're going to be using. Basically, whatever max current you want to put in. Now, this does not apply to A123 cells, headway cells. A lot of the smaller packages will do 40, 50, 60 C for a few seconds. These won't. They'll really do about 3C. I've also read some hysterical accounts that you will absolutely kill yourselves if you run them at 3C. We always run ours at 3C. That's the design criteria. The Speedster Part 1, if you go on the freeway and you accelerate to 70 miles an hour, you've been at 540 amps for 20, 30 seconds. That's what it takes to get there. That's at 110 volts. If I could do 500 volts, it would be at 100 amps. That's the calculation. So that's a little bit about sizing them. They will do 3C. And in fact, what we're going to do now is test each of these cells and compare them at the 1C rate. These at 200 amps for an hour, basically. These at 180 amps for an hour. And these at 160 amps for an hour. Now let's talk about how we might do that so you can duplicate it yourself if you want to do this at home. This is a couple of Acme Electric Power Products Group PS2L1500 loads. Whenever I see Acme, I think of the Wile E. Coyote's Acme kit with the rocket that he's always lighting to catch the Roadrunner. These are two 1500 watt constant current loads, and we've talked about constant current chargers. There's such thing as a constant current load. I can dial in a current level, and whatever happens to my battery voltage, it will maintain a resistance to continue that load at that current rating. I've actually added a second one recently, have them strapped together so I can do 3,000 watts. 3,000 watts would be, well, 3 volts times 1,000 amps, or 30 volts times 100 amps. In this case, there is a lower threshold of what this thing can do resistance-wise and maintain that constant current. So it can't really do it on a 3.3 volt cell. By putting them together, I've got about 6.7 volts, decreasing to 4 something at the end of the test, and it can maintain that load factor that whole time. When you do this, you can't use battery clamps, alligator clips, so forth. You have to use, just like in your electric car, terminal lugs that are bolted together. We're using some 1-AUG cable and some 1-aught welding cable in this setup. I've got a power supply here, a Lambda EMS power supply. This thing will only do about 11, 12 volts, but it'll do a couple hundred amps into the battery. And with this load, I can take a couple hundred amps out of the battery. And in fact, probably next week, I'll show you how to do some 3C testing. We're actually going to do some pulse testing, simulating a drive at 3 times the rated capacity. In this case, some 600 amps. Actually, we'll use the 100 amp cells, so it's a little less. Do 100 amp cells at 3C, it'd be 300 amps. 90 amp cells would be 270, that sort of thing. But you have to have this thing kind of rigged up with bolted terminals, just like in your car, or you're going to melt cables, and I've melted dozens of them. Try and do it otherwise. You wind up, you just have to bolt all this together. So I've got a 200 amp power supply, I've got a 200 amp load. Here's a voltmeter. This is an Agilent 5.5 digit voltmeter. Nothing magic, it's a good bench voltmeter. It doesn't really matter how ultimately accurate it is. I just need some precision to do the relative voltage measurements to several digits. And that makes it easier to record them. This is a traceable control company, digital thermometer. It's about 350 bucks. Its advantage is it's quite accurate. And if you go to looking at voltmeters or at thermometers and so forth, don't ever go shopping for one in a store where they have a whole wall full of them, because since all of them read something different and they're on the same wall, you'll lose confidence in thermometers entirely. But this is pretty accurate probe thermometer. And we're going to measure, one of the things that comes up is when you do 1C or 3C charge and discharge on these cells, what's the heat gain? How much heat do these cells actually throw off? And that's one of the big things we're going to be investigating with our 1C charge and discharge, is to determine the heat gain of the various cells. And what that's going to tell you is what you have to do in your car to keep from overheating the batteries. As it turns out, I'll give you a little peek into the ending. You don't have to do anything. These cells operate fine up to 85C, which is 170 Fahrenheit or so, and you're not going to get anywhere above about 140, no matter how you abuse these cells. So the heat gain is not tremendous. in a situation like the Mini, where we have an interior box enclosed, that would be a problem because the heat will build up. But as long as you have some place for it to go, these cells are actually quite well behaved temperature-wise. I talked to you last week a little bit about our contactor box. This is closed up now, is our contactor, the dual gigavax we're going to use for Speedster's part duh. I've got that connected to the positive terminal, this 200 amp cell. Now the other end of it goes to the positive terminal of the load. I've got the a little switch here, another power supply, 24, got it set for 24 volts. If I hit this switch, I connect those cells to that load, and if I shut it off, they're disconnected, and that's all I have to do that. This device here, let's talk about that. I made it. I hate to bring this up. You're going to want one. I don't have one for you. I don't have this one finished. In fact, they're a mess, but they're actually pretty cool. This is an Arduino Mega. This is basically an Atmel 1200 series microcontroller that some guys in Italy put on a little board and just extended all the pins to the edge and put these connectors on it. They put a little power supply on it and a UART with a USB bootloader. That package with a little power supply and that bootloader allows you to load programs in Flash for this microcontroller and run them. And it has lots of digital inputs and outputs, pulse width modulated outputs, analog to digital inputs, digital input outputs that can go either way. They've just extended the chip to the edges of a little card. And they did a, well, they call it an integrated development environment, an IDE, but it's basically a little editor that you can do. It's like C++ for kids. It's a little C++ compiler for the Arduino, and it not with a full C++. It doesn't have the standard libraries and so forth, but a C++ syntax with a couple of special commands to read pins and write pins and so forth. So this is a great little device in that it's cheap. These cost $50 for the board. And there's a body of people out there doing stuff with that you can find code and things to do things. So that's the Arduino. This is a earlier model I had. A couple of terminals with a copper bar, 20 millimeter by 10 millimeter copper bar, stood off from the aluminum with some high molecular weight PVC, and this little device. I've got it on here. It's got a hole in it. It slides up and down the bar. It's called a LIM-HOS Hall effect current sensor. As current goes through the bar, the magnetic field will induce currents in this Hall effect device, and we provide 5 volts from the Arduino to the Hall effect device and can get a 0 to 5 volt output based on the current. This is a 50 amp LIM-HOS. It's good up to about 200 amps, plus or minus. I also have a 150 that's good up to about 600 amps, plus or minus. The 50 has a little better resolution. The 150 has a little better range. And so in this one I have both of them. And I read them and determine which one to use based on what current I'm reading. Why do we want to do all this? Well, the conclusion I've come to on state of charge on these cells is that voltage, temperature, your goofy kid BMSs and so forth are not going to tell you state of charge. You can count amp hours in and you can count amp hours out. This little microcontroller, I've got a GPS connected to it. It puts out speed and your location. I can put Bluetooth to it. There's a lot of things you can hook up to it. This is a serial LCD. I can simply paint data to it. If we measure the current through those limb hosses about 3 times a second, and we count how much of that third of a second actually went past between measurements, and we sum that together, over time we will integrate our amp hours in both directions. And so I can determine state of charge. I've got a temperature probe on here. But the way this is set up, I can do amps, amp hours, state of charge, and temperature. Try to see if you can get a shot at this display. It's a serial LCD hooked up to the Arduino that just lets me check that. I've got a switch I can press and zero out my amp hours and my amps. Now, why do I need to do that in this case? I've tried graphing this by time. I take a little iPhone or something and every 30 seconds write down the voltage and so forth. It's hard to do that accurately by time. I can watch this and tell how many amp hours have gone by in whatever time and do it by amp hours, and it's a lot easier. So what we're going to do is, because I can count amp hours, I'm going to write down the voltage and temperature of this every 5 amp hours for 200 amp hours, 40 measurements. This is going to take about an hour. And then I'm going to turn around and after I've discharged this battery completely to 0, and you probably don't want to do this to your batteries if you want to extend their life or testing, we're going to turn around and charge them immediately at 200 amps. And I'm going to again write down the voltage and the temperature with this temperature probe shoved down between the 2 cells. We've got I'm showing 91 and falling. I just did a thing. We're at an 80-degree ambient right now. And let's see if you can see this. If I turn this switch, I'm showing 199.9 on there. On my little Arduino, I'm showing 200.6 amps. You can see my amp hours counting. The temperature's not hooked up to anything. It's laying on the floor, 77 degrees. And my state of charge counting down. What we're going to do, let me shut that off. We'll zero this out. I'm not terribly interested in the capacity of the cells. I've already tested them. These do right at 200 amps, amp hours. These 180s will be a little higher, 184, 185. The 160s are not young. they'll be right at about 158 or 160 amp hours. Those have been used. They're 18 months old. But by doing these at 5 amp hours, every 5 amp hours, these every 4.5 amp hours, and these every 4 amp hours, we're doing exactly the same percentage measurement based on the capacity of the cells on all 3 of them. In other words, 5 amp hours is 1/40th of the 200, and 4 amp hours is 1/40th of the 160s. And that'll let me line up the graphs when we get done and do that. The voltage measurement, I'm going to measure the 2 voltages. We're seeing 6.63, and then I'll divide that by half for an average cell voltage. I know you're all worried about balancing and so forth. I can't tell you how I'm not, but this one right now is at 3.31 and 3.32. You know, they're a little off at the top. I've taken out 4 or 5 amp hours already out of these, but we're gonna run the test and show you the temperature gain and the discharge curve by voltage taken every 5 amp hours. And as I watch this tick over 5 amp hours, I'm going to write down this voltage and this temperature. And I'm going to do it at 5 amp hours, 10 amp hours, and so forth. So let me zero this out. I'll get me a little pad of paper. And we're going to start at 6.6486 volts and 80.782 degrees Fahrenheit. Now, how accurate is that? I don't really care. I'm looking for the resolution. It's going to be as accurate at one measurement as it is at the next. And so it's a relative thing. It doesn't matter whether it's to a NIST voltage standard. It matters if it's changed from 1 minute to the next. And so these are relative measurements, but I can use the resolution when I put together the graph. This is a very manual way of doing it. I know there's more automated ways. In fact, I can use the Arduino. It comes in here. I like to see what's happening so I can reproduce it later, and often questions come up. Reviewing data that the computer did, a lot of times I don't know what it really did. So that's why we do it this way. So we'll turn this on with a switch. You should be able to see here our voltage is falling. I've got 99.9 and 100 there. Reads 200.63 here. And I'm counting down. I've spent endless hours calibrating this Arduino, both to the power supply and these loads. It's pretty close. So we're right at a 200 amp hour rate. You see my amp hours counting down. Trace, see if you can get a good tight shot of this Arduino box here so they can see what I'm doing. Can you see the numbers? Great. So we're counting down our state of charge and our amp hours. What I'm really looking for is the amp hours. I can sit here and watch this. We just crossed 3 amp hours. Here our constant current loads are maintaining the load. Of course, the data I'm looking for is the voltage and the temperature. And so at the end of 5 amp hours, I just sit here and watch this. Kind of like watching grass grow. We're just crossing 4 amp hours. Voltage changes faster than temperature. So as soon as I get here, I'm 496. There's 5. I got 62427. 6.2427. And then my temperature, 81.010. And our next increment is at 10 amp hours. And so we're going to sit here and wait for it to get to 10 amp hours. Understand this takes 2 hours to run this test all the way to 0 and back, and we have to do it 3 times to do the 1C test, which is why this is not the most fun work in the world. It's easier to just make Excel graphs. However, things happen. We see oddities. For example, when I did this test before, the temperature went up as I discharged it. When I started to charge it again and reversed it, would you believe the temperature goes down for the first 4 or 5 steps and then starts continuing on up? That's a phenomenon. It means something. I'll figure out what later, but if I'm not standing here doing this, I don't know that it does that. I'm not too sure why it does it at this point. It's not a big change, 2 or 3 degrees, but it's an interesting thing. Those kind of observations are usually where new discoveries come from. And sometimes old discoveries are rediscovered. And that happens a lot in batteries. Again, these are not lead acid cells. There's my 10 amp 62281. And 81.485, and I'm going to write that down. And we continue doing this. I'm not going to make you stay with me the whole 2 hours. We're going to write these down and then show you the charts at the end. But this is the process. You can duplicate it. You need a load that'll maintain a constant current level so you can measure the voltage change and the temperature change. You have to use cables with good connectors, bolted down, not alligator clips and so forth, because we're doing 200 amps out of this thing at 6 volts. That's 1,200 watts or so. Right now, but it's enough power that current levels, these cables will get warm, and I've actually melted some when I tried to do even the big clips, like you know, a battery booster cable. They're not meant to sit there for 2 hours with 200 amps on them, even if they're rated for 200 amps. And here we come up on 15 at 1480. And we got 62208 and 82.197. And there's no more magic to it than that. We're just writing them down on a regular interval. In this case, we're running at 200 amp hours. We're running every 5 amp hours. And I can count that using my Arduino. And that's the trick. And we're going to write it down, put it in a Microsoft Excel spreadsheet, and graph it. I will have the graphs and the spreadsheets available for your download and perusal. There's no secrets here. We're not selling anything. We just want to find out how the batteries work. And so that's how you test the battery. If you're curious how it works at 1C, this is the process. Put it under 1C. And do the measurements. Talking about it online, theorizing what might happen, almost everything I've thought how these batteries ought to work hadn't turned out to work that way. We carried a lot of lead acid thinking with us. There were a lot of factors about lead acid batteries that had to be taken into consideration. They just didn't apply to lithium iron phosphate cells, as it turns out. And there's 20. I got 62151 and 83.137. And so we're already establishing a temperature climb as we take 200 amp hours out of the battery. Internal resistance. I don't know if I've got my calculator with me, but this is pretty easy. People talk about it. The problem is it changes from the beginning of the draw to the end. But we were at 6.6486. Let me enter that in the calculator. 6.6486. After 5 amp hours, we were at 62427. If we subtract those, we get 0.4059 volts. Divide it by 200. Amps. And you get 0.0020295. That is 2.029 milliohms, about typical for these cells. We're coming up on 25 and 6.2101 and 84.205 Fahrenheit. Okay, let's zoom in on this. We're coming up on 140 amp hours taken out of the cells. That corresponds to just about 70% discharge on our Magic Arduino. And we can see we're right at 6.0015, and we're starting to drop off a little bit here. As you can see, the voltage counting down. Our cells are pretty even at this part of the curve. I've got 3.027 maybe, and 3.035 on each of the two cells. For a total, we're just going under 6 volts, 5.9940. Our temperature's up to 110.688 Fahrenheit, and that's about a 30 degree Fahrenheit increase, or temperature gain of about 30 degrees, while we're running 200 amps out of the cells for 3/4 of an hour at this point. So we're coming up on 160 amp hours on this 200 amp hour cell. And that represents our 80% mark depth of discharge. We'll take our readings here, but we're at 5.8802 volts So that's, you know, well under 3 volts per cell. I'm at 115.292 degrees Fahrenheit. So we've had a 35-degree temperature gain to 80% depth of discharge. And that's about as far as you want to take your cells driving them at 1C. Recall that our spec sheet said we could go down to 2.8 volts, which would be 5.6. But that's at the standard discharge rate is 0.5 C. We're doing it at 1 C. We'll be considerably lower than that when we finally cut it off. You can see on the curve, and I've already done the curve. We've run this test, and I'll show it to you a little bit. We're here at 160 amp hours on the thing. I'm going to display that chart over here. You can kind of see where 70 and 80% at 140 and 160 amp hours comes in. You were still on the flat part of the discharge curve. We start out here up, you know, 3.35 volts. As soon as we do the first 5 amp hours, it drops to about 3.15 volts. And then it maintains that down to 3 volts, a 0.15 volt, very gradual decline on a very flat thing. But as we get past the 180 mark, our 5.81 volts, you can see it's counting down pretty quickly now, and that will continue to accelerate, and as you see on the chart, until it drops off the planet here and goes into a dive. This is the danger area for these cells. They can be hurt overcharging them. Let me dig you up one of my trophies here. This was actually done at a very low, about a 8 amp charge. And but if you will do that for a couple hours while you go off and talk to a daughter with an emergency and forget about it completely, you'll find that these cells do quite melt down. I had this up in the bedroom playing with the Arduino and just kind of calibrating it and trying to get it to drive a 50-year-old Porsche style fuel gauge, which I think we're going to be able to do in part duh. But I managed to burn through some carpet, put a little char on a wood floor, and fill the room with a very noxious kind of a vapor, kind of a sickly sweet smell. Nothing horribly irritating, but I had to air the place out for a day before we could sleep there again. So this is kind of what you can look forward to, but even low current level overcharge. But that's fairly unusual. That's if you leave them. So if you depend on a cheap charger and a BMS system to cut it off, you really need a good programmable charger that you can rely on to cut it off. That was on a very inexpensive 10 amp 12 volt power supply that I just had hooked up to it, and walked off and left it. The more common death on these cells is cell reversal. We put them in long series packs, and we charge them typically at 15 or 30 amps. As long as you don't overcook them like this, you're not going to hurt them too bad. We charge them at an average voltage. On the Thunderskys, we've been using 3.65. They've lowered that to 4 volts. I don't think we need to make a change. I rarely see a cell reach 4 volts when we're charging them to an average of 3.65. And note, I'm famous for not balancing, and certainly not for top balancing. And the reason that you don't want to top balance is because that puts the differing capacities at their most extreme at the bottom, which is where we're going now. We're at 175 amp hours on a 200 amp hour cell, and we're clocking down pretty quickly. If you have wide extremes of capacity on the cells, it shows up on the two ends. If you top charge them, you're actually lining them up at the top and exacerbating the differences at the bottom. Now, why is that important? We're drawing 200 amp hours out of these cells. Next week, I'm going to try to show you some 3C tests where we'll be doing 3 times the capacity, taking energy out of the cells. If they're in series and one of them goes off this cliff ahead of the other ones, it'll drive to 0 volts, but your pack will not discontinue producing current. The other cells will drive current through that cell in what's called cell reversal. If you drive it to 0 volts, sometimes you can get them back if they just kind of touch there. If you actually drove them down into cell reversal, they never come back. They're 0 volts, and they're essentially a $240 doorstop. They don't tend to burn up like the overcharge condition, unless you carry it to extremes. I haven't had them go that far. But if you drive them down to nothing and they go into cell reversal, that's the end of that cell. It goes to 0 volts, and rarely can you get it back. If you can, you'll typically have 2/3 or 3/4 of your original capacity, and now the problem gets worse. It's best just to replace the cell. But that's the standard death of a lithium-ion cell is through cell reversal, with the other cells driving current through that cell because it went off the discharge cliff first. When we're driving the car, 200 amps out of a 200 amp hour cell is moderate duty. 600 amps is if you're accelerating hard, you know, in the car. And that's kind of the range that occurs in. The damage is much more extreme at this end of the charge curve than up here where you're charging at 15 amps. And so the debate about top balancing is only a debate in the minds of a few people that are typing themselves furiously in these things. We've learned to, if you have any interest in balancing, to balance them at the bottom where the damage can be done, and the top doesn't matter at all. So these guys with the shunt balancers at the top, it's not just that they're not doing anything useful, they're actually harming the battery packs. Again, we live BMS free one day at a time. We can take a look at our voltmeter here, and we're at 4.86 and dropping pretty quickly. I'm showing 187 amp hours on the magic meter here. If you take a look at the laptop here, Trey, see if you can get a little shot of that. I don't know if they can see, but I've actually got a little screen where all the data from the GPS I've got in the Arduino, amp hours, voltages, the whole thing is scrolling up. I can set different parameters for this, and I just kind of left it at 100 amp hours, which was some other cells I was testing. We're at 190 now. I'm at 4 volts and falling. That's 2 volts per cell. And we're at 124.8 degrees Fahrenheit. I'm going to go ahead and let this run all the way to the end. We're going to see what we wind up with here. Again, I wouldn't expect to use these cells very much in a car after this kind of treatment, but we're about finding the end of the rope here. And I think we can do this and reach 200 amp hours, although I tested out 5 or 6 amp hours playing with the switching before we started. I think we'll reach 195 or 200. I'm at 3.33 volts and falling like a stone. We're at 126 degrees Fahrenheit, or a 46 degree bump. When I ran this earlier, I think our total gain on discharge was 48 degrees Fahrenheit. we pick up another 23 degrees of additional gain when we turn it around and do the full charge. Our cell voltage is dropping, and our current loads are struggling to keep up at this point. So we're about done at 196 amp hours. I'm at 2.78 volts and dropping. My current's dropping off. I'm showing 170, 167 amps. We're pretty much tapped out here. Let's see if you can get a shot of that, Trace. $197 amp hours. That's close enough for government work. So these packed 200 amp hour cells, I'd say we got the 200 amp hours. Like I say, I ran 300 or 400 setting up the thing before we started. I'm at 2.45 volts. That's on 2 cells. So we're talking about 1.1 volts per cell, and it's diving like a stone. So we've got the good out of these batteries. I'm going to shut this off, and we're going to watch something kind of interesting here. Trace, I want you to get a shot of this. We're at 131.58 degrees. That's a little bit bigger gain than we had the first time around. Let these go. But now my voltage is climbing quite rapidly under no current load. And we've simply shut it off. And in fact, I'm going to shut these off. They'll draw a couple of tenths turned all the way down. So here we go. We're at 4.8 volts and climbing. Over the next 4 or 5 minutes, this should climb up pretty smartly in the 5.5 volt range or so forth. Let's give it a few minutes rest, and we'll come back and see what we've got then. And then we'll start our charge cycle. All right, we've got our loads off. We've run out 198.85 amp hours, and we've let her set for about 5 minutes, and our voltage has climbed back up to 5.4740 and counting up volts across the 2 cells. That's 2.75 volts per cell. So they're at the bottom. At this point, I could simply put some voltage in one of them. This one's 2.635. This one's 2.85. So I could put a little charge on this one and bring it up to be the same as this, and that would be bottom balancing. I'm not going to bother on these 2 cells. But that's what you would do, and believe it or not, since we're on the steep side of the curve, 3 amps at a minute and a half would do it. It doesn't take hardly anything to move that and to balance those 2 cells at the bottom. And that way, when they go over the edge of the cliff, they kind of go over together, and one can't drive the other one into reversal. So we're at 5.5 volts here. We're going to turn around and do something different. We're showing almost 140 volts, 140 degrees Fahrenheit on our temperature. That's pretty near a 60 degree gain. I think I showed 48 degrees the first time. It's an 80 degree ambient today instead of a 70. And we were driving it pretty hard right there till the end. We're going to turn around now. I'm at 139.926. I'm going to turn on this power supply. We're going to hit our contactor again and hook it up. And I'm going to adjust this for about 200 amps. And Trace, let's see if we can get a shot here of our Arduino. We're showing 200 amps of charge, and more importantly, our amp hours are now clocking down. 197.053 and then 196. Then we're going to count our amp hours backwards, and we're going to count those down to 0 on our charge cycle. Now, that brings up something about quick charging. We're charging at 200 amps, and I'm still at 139.902. Here's 139.89. I mentioned there's a little dip. You can see it in my chart here. When you start charging, your temperature goes down for the first 5 or 6 increments of 5 amp hours a piece. And we didn't quite get there, so we count 195 and then go 190, 185, just like we did coming down. But my temperature is actually dropping slightly as I charge at 200 amperes. Let me adjust that for right at 200 on the old Arduino, which I can actually, I've got the 200 on the power supply. I've actually got 2 more digits on the Arduino display than I have here, and I've been back and forth 100 times. I've got it dialed in pretty good on here between the loads and the power supply. It's pretty accurate. So we're charging at 200 amps. We'll charge these 2 cells in right at 1 hour at 200 amps. And we'll write down this voltage. We're up to 6.55 right now, all the way back up. And you can see our charge curve. We immediately go up to, about 6.7. This will climb very rapidly up to about 6.7. And then we go into the flat part of the charge curve. But at the end, I'm going to take it quite way up above 4.25 per cell. How can I do that? We just said that they've dropped it to 4.0. 4.25 used to be the thing. I'm going to charge this cell in an hour at 200 amps. I've thrown the charge curve out the window. If I wanted to do this by charge curve, I'm going to charge at full current, whatever I can muster, in this case 200 amps, until the voltage gets to, in this case, 4.00 volts is the new charge curve they've given us with the yttrium cells. And that would work fine. And I would hold that until it tapers off. But I don't really have to do that. There's no magic to the voltage. Just as there's no magic to the voltage coming down. Yes, 2.8 volts is the cutoff at 0.5 C, but we were discharging at 0.1 C. It's going to be considerably lower there. These things are related. The voltage and the current and the resistance, it's Ohm's law run amok. They're all tied together. Voltage being the easy one for you, but it's not really the driving one. It's energy into the pack and energy out of the pack. We will not damage this cell until we put in more than 200 amp hours into the cell. And if we do that very slowly at 10 amps, we can burn it down, and had I not gotten back into the bedroom in time, I could have burned down the house. At 10 amps, because I was putting more energy into the cell than there are lithium ions to recombine. And at that point, you start to oxidize everything. It's going to get the electrons from somewhere, and you simply overcharge the cell. Since I have an amp hour counter, and I know that there's a little bit of inefficiency, not much. Surprisingly, I've calculated this at about 99.2% efficient going out to back in on these charge-discharge cycles. And I've got just a little bit of a fudge factor in the thousandths built into the Arduino. But if I put that 200 amp hours back in, all 200 aren't going to get there, and I will not have a fully charged cell, but it'll be real close. We could then give it a rest, do a standard 0.5C charge curve to 4 volts, and you'd see that it'll take about another 1 1/3 or 1.5 amp hours after I put the 200 back in. And that's pretty much how it shakes out. So by counting amp hours, I really don't care what the voltage is on the cell. The voltage was never what overcharged the cell in the first place. It hadn't got anything to do with it. The voltage and the current on a standard constant current, constant voltage charge curve are a handy way and a good way, and the way I want you to use to charge your batteries. But as we get into quick charge, and really just determining state of charge, increasingly, we're going to have to come up with some ways to do this amp hour counting. Let me show you a couple of devices that are relatively inexpensive. They're not problem-free, but they kind of work. Let me grab them. This is kind of interesting. This is a thing called a TBS Expert Pro. And see if you can get a shot of this, Trace. This is a little kind of a cheesy meter with some buttons on it, and it operates with a little shunt, and it will count amp hours in and out. It's kind of limited to 35 volts DC, but you could use a little divider to divide down your pack to monitor the voltage, or just monitor the first 10 cells in your pack, and that'll give you a little voltage indication. But the big thing is it'll count current and amperes. It's $500 and something, comes from the Netherlands. Canadian EV is handling these. This is an entirely different device. This is the Xantrex Link Pro. It used to be called the Link 10. A little more advanced than the Link 10, not much. It counts amp hours and amperes. In fact, if you take a look at them, they look like the same device from the front. If you turn around and look at them from the back, they look like exactly the same device. Now remember, I told you I had 2 completely different batteries under TS LFP 200 AHA. In this case, I've got 2 completely different names, but they're the same device. I think the Xantrex is about half the price of the TBS. I think this is $500 and something. This is $285. They're kind of cheap amp hour counters. They have a kind of a cheap shunt. It's a 50 millivolt 500 amp shunt, and it doesn't look like it would hardly carry 500 amps. Understand, you can use any 50 millivolt 500 amp shunt. 50 millivolts, that's the voltage reading you would get across the shunt at 500 amps. You can get one a lot heavier, a lot nicer shunts. You pay a little more for them. They work with these just fine. A 50 milliamp, a 50 millivolt 500 amp shunt is a 50 millivolt 500 amp shunt. The heavier ones often are a little bit more accurate. So this is a couple of devices you could use for amp hour counting. That's about what they'll do. They'll do voltage and some other things. They're really for solar systems. and that's why they're kind of limited in voltage. But by counting amp hours, we can recharge these batteries quite rapidly. Realistically, how would you do this? You know, I would have my mother bank of batteries, or my, as I said, Manzanita just announced a 225 amp charger. You have to have 3-phase power to your garage to use it. But I mean, there'll be people getting that as this electric vehicle thing moves along. And 225 amps will charge our Speedster Part Duh, for example, in less than an hour, 40 minutes, something like that, off of without even a battery bank. So we're gonna. I think this is gonna happen. The quick charge is gonna be available, but you have to do a little bit different dance with it. I would charge it up to, let's say you don't discharge more than 80%. You take out 160 amp hours. Well, you know, put 140 back in, and then plug it into your regular charger to put a, you know, the last 20 amp hours if you need it, or go drive the car. Again, not overcharging it is the trick. It really doesn't care how fast it's charged. There's some indication from the manufacturers, and I don't think, you know, the way they phrase it, I'm not sure they know. It kind of makes sense, but I'm not sure they've demonstrated any of this, that at higher currents, and they state that you can charge these cells at up to 3C. This 200 amp hour cell, you can put 600 amps in it and recharge it in 20 minutes. They do indicate that there's probably some decrease in cycle life in doing that. So it's not something you'd want to do every day, but to do it on occasion or even semi-regularly, certainly at 1C, and do a 1-hour charge would not be, you know, a problem. To be safe, why wouldn't you put in, you took out 160, put 140 in, and then if you're not, if you've got a little time, put the regular charger on it. Otherwise, go drive it and bring it in that night and put it on your regular 20 or 30 amp, basically trickle charge, and let it charge overnight to the proper top charge, and it'll be fine. So that's part of the demonstration, is temperature, and that you can, in fact, charge the cells. We have now reversed our thing and continue our climb on temperature. And right now I'm showing 141 degrees. That's a 61 degree temperature rise from the start of this exercise to the stop. When I ran this the previous time at 70 degrees ambient, by far the huge part of the temperature gain was at on discharge. We had a discharge gain of 48 degrees Fahrenheit, and then a further 23 degree Fahrenheit gain on the charge. So charging doesn't see, even at the same current rate, does not seem to cause as much temperature gain, or as much further temperature gain as the discharge at 200 amps. The let's see, here is our 160 LFP charge discharge curve. It's really quite similar. I don't see a whole lot of difference that the yttrium makes in charge discharge curves or in the temperature gain. Again, we had 42 degree Fahrenheit rise in the discharge segment, and an additional 13 degrees on the charge. Here's our Sky Energies. They seem to be a little kinder on temperature. China Aviation Lithium Battery Company is a new name after the 1st of January. And we only had a 27 degree Fahrenheit gain on the discharge at 180 amps, and a further 21 on the charge side. And so that was that. what I've done by doing this at 5 amp hours, these at 4 amp hours, and these at 4.5 amp hours, and these at 4 amp hours, they're on the same increment. And so now I can plot this by percentage. And here is a graph, LiFePO 4-cell temperature gain in Fahrenheit during a 1C continuous discharge. And you can see that the LFP 200A, the one that's putting the most energy in the same volume, has got the highest temperature gain on discharge. And the China Aviation Lithium Battery Company, the middle one, has got the lowest. Here is the temperature gain during the charge cycle. And here they're a little bit closer because there wasn't that much of a change. Again, the 200 amp hour had about a 26, 27 degree climb. Oddly, the 160 had some erratic temperatures. I don't know if I had some winds blowing through here or what, but it seemed to have the least. And then I was also able to compare the charge curves. And there's really not much to say about them. They're really quite similar. The China Aviation Lithium Battery Company, or Sky Energy, has a little flatter curve. Of course, it typically goes to 3.6 volts instead of the 4 volts. But just the curve is a little flatter. I like that about those cells. It makes it more difficult to determine state of charge from voltage, but we've kind of abandoned that anyway. And so that's the comparison there. And then here's a discharge curve comparison. Again, you have a little more sag in voltage from the 160s being the greatest, the 200 Thunderskys the next, and your flattest curve is the China Aviation Lithium Battery Company. And that's the old Blue Sky Energy cells. I'm going to put these graphs up on the blog, and I'm also going to put the underlying data, the spreadsheet itself from the Microsoft Excel spreadsheet, the actual data that I recorded for each of these 3 cell types, all the way down and all the way back. You're welcome to the data and the graphs. Anything you can do with them that's useful, I would appreciate. I do like to get data and conflicting data from our viewers and from other interested parties. I know there's other people that test cells. If you want to make prognostications about cells and pontificate about your theories about them without any data, I got to tell you, it's just, I've been doing this too long. I'm not interested anymore. They're not interesting. You know, tell them to somebody else. If you have a new idea with some new data, I'd love to hear about it. But it should be something that I can duplicate somehow. And I'm not above buying test equipment or whatever necessary to do that. But, you know, if you want to confer, we have to be able to not only carry the data back and forth, but we have to each be able to duplicate the results. I'll be happy to help any of you all describe in gory detail how to do these, or how I tried to duplicate yours and either succeeded or failed. But that is the collaborative scientific method. Proclaiming yourself a $200 expert and assuring me that you know a lot about it, I'm just too old. My knees don't work anymore. I can't do that. It's not even entertaining. If you're trying to sell something and you want to get me to bless your charts without looking at the data, I can't do that either, Andy. I'm sorry. You're going to have to sell battery management systems using fake data somewhere else. I can't play. But these are fascinating batteries. I've become a big fan of them. quite beyond the very interesting chemistries that are being developed here by U.S. companies. I can't get access to the batteries, and they do not appear to me to be as robust. You can get more power quicker out of those small cells that Tesla uses, but I don't want to do all that and I certainly don't want to deal with the heat. This test has been mostly about temperature, but to show you that you can take energy out of these cells at 1C. You can put energy into them at 1C. You can do it safely. It doesn't harm the cells at all. It doesn't harm your equipment at all. It doesn't harm your car at all. And next week, I'm going to do some perhaps more limited testing of 4-cell packs. I've got some Thundersky 90s and some China Aviation Lithium Battery Company 100s. And by stepping up to a 4-cell voltage, I can run 3C. And we're going to do a pulse test. We'll take out a couple of amp hours in a pulse and then let it rest for a minute. And take the voltage after it's rested and take it after it's taken a couple of amp hours out, and do that 30 or 40 times and do us a little sawtooth diagram to see what voltage sags we see at 3C and what the temperature does under those kind of loads. That'll be a little bit more of a simulation of a driving experience. 30-second or 1 minute acceleration drive cycle, and then 30 seconds or a minute no load. And I think that'll be kind of interesting, both with regards to temperature and the amount of amp hours we get out of the pack and what happens to our voltage. And you'll start to see why some of these voltage monitor BMS systems don't make a lot of sense to me. I'm not sure what you're monitoring for, and if you achieve that, what you would do with the information, which is what I've said all along. And so we'll take a look at some 3C testing later. Meanwhile, the graphs and the spreadsheet are available online. I invite you all to examine them, critique them. Yes, I'm a little ugly. My mother dressed me funny. I probably did it all wrong, but you know, show me the error of my ways, and it's pretty easy to rerun the test. And if we think it'll come up with any different result, I'm not above doing it. So that's pretty much our battery test segment for this week. It's mainly to introduce you to these graphs, temperatures, and voltages. I'm at counted down to 122 amp hours here. We'll follow this, bring you back in at the end, and I'll show you where we're at then. I'm at 6.98 volts. We're up to 144.9 degrees Fahrenheit. This spank, and so it's going pretty well. Alrighty, we're about 5 amp hours away from being fully charged. I've got 8.28 volts on here, which is 4 and a dime or 4.15. Interestingly, with the clamps this time, to clamp them together, we've generated quite a bit of heat, 162 degrees Fahrenheit, and that is an 82 degree total gain, which is 20 degrees higher than when we were measuring them before with simply the probe on top of the cells. And so with the probe down between them and the aluminum plates, which are quite warm, I'm measuring 162 degrees. We're putting 201 amps into the cell. I'm at 1.9 amp hours. We're coming up here on 8.5. So it's all pretty much come together. We haven't even really exceeded our voltages very much, although these are 4-volt cells now instead of 4.25. We're still putting in 200 amps, and that's pretty much it. I'm down to 0. I'm going to shut her down. Again, you don't want to overcharge them. I can now, if we watch this, this cell will start to fall over the period of about an hour, hour and a half, it'll get down to about 3.35 volts per cell. At that point, if I wanted to, I could put on a, in this case, a 100 amp charge, or even a 50 amp charge, and do my constant current, constant voltage curve, and top that cell out quite nicely. But we've basically taken 197 amp hours out of the cell. We've put them back in, and we're at 100% charge. And we did that in an hour, basically, at a 200 amp hour rate. We did have a, well, we're up to 165. Our temperature is still climbing. And so that's about an 85 degree rise above ambient. Our operating temperature for these cells is 85 degrees centigrade, which is about, let's see here, 1.8 times 85 plus 32, about 185 degrees. We're still pretty well within range. And so, again, my experience with these cells is if you have them in boxes exposed to the airflow, if you're drawing 200 amps, you're also going down the road and blowing air over the boxes. If you have a very large box with cells at the middle, you have to provide a way for that excess heat to get away, to get out of there. These are pretty much exposed. We don't have any wind in here, so we don't really have any airflow. But as in the case in the Mini, we've got a box that's out of the airflow and has 55 cells. That's why we put a fan on it with a temperature controller. It'll just come on if they get hot. So far, interestingly, they haven't gotten hot. We've been out on the highway at 80 miles an hour, and it still hadn't been a problem. But at those voltages, we're barely pulling 100 amps, worst case on the freeway. Lower voltages, if you're pulling higher amps, you're going to have more of a temperature problem. Again, if you've got the cells down in the airflow, it should work out pretty well. But if they're totally enclosed and are not getting any cooling, you need to make provisions for that. A liquid cooling system, such as they have for the small cells in the Tesla or the Mini, I just don't think it's necessary. Put you a fan, pressurize your box, and these little channels are your friend. You can drill slightly more holes in the center of the box than you do around the exit. Pressurize the box and have those be the escape. You'll be able to direct a little more flow toward the center of the pack that way. But generally, these cells are very temperature forgiving. We're down to 6.8 or 3.4 volts already on this brand new Andy Thundersky 200 amp hour cell, and it's falling pretty smartly. That'll trail off, but I'll come in tomorrow. That'll be about 3.35, 3.7 volts. So that's pretty much the story on 1C charge, discharge, and charge. We're going to put the graphs up on the website, I guess on the blog, where you can download them and get the Excel spreadsheet data. But that's the story on 1C charging of 200, 180, and 160 amp cells. Again, they'll do it. The next time we're going to show you some 3C work, and it'll do it just as well. With the pulse, we won't have any more temperature gain than we had on these continuous 200 amp cycles. And that's a pretty strenuous workout for a battery. Full discharge and a full charge, 1 hour each. We've given them a workout, and they're still ready to go to work. So I'm a big fan of these cells. I think they're what makes an electric car viable. Again, an electric car is a car that you would not park next to a gasoline pump and have any business being there. And so I think these batteries are what's making it viable for the first time. Again, next week we'll take a look at some 3C work. But for now, that's a 1C discharge and a 1C charge on 3 different cells, pretty much by the same manufacturer, I'll admit, and very similar charge and discharge curves. Not much to learn between them, but that's some knowledge in and of itself. You're not going to go wrong with either one of them. We're seeing a little more power in the same volume, and that's important in a car, in the Thundersky yttrium cells. I like the charge and discharge curve on the China Aviation lithium battery company cells just a little better. And the rated lifetime is tough to tell, but they're claiming higher numbers here on the Thunderskys. I'd call it about a toss-up between them. They're about the same price. You can pack a little more range in if you specify the TS-LFP 200 AHA cell, but you kind of have to call David Coy at EV Components and specify it, because it's exactly the same part number as the bigger cell that has the same amount of space, or same amount of energy. So for Jack Rickard and EVTV, that's another week of watching paint dry and charging and discharging cells. This is how you do it, and I'm very open to any data you might have. If you have an opinion that all of this is wrong, start a TV show and air it. If you've got some data or want to discuss anything about these cells, I've become a big fan of them. I'm kind of pushing the concept that we all ought to be driving electric cars. That's the ones that don't get parked next to the gas pump. And this is how you do it. It's always been about the batteries for 100 years. We've got them, and they're getting better. 25% gain, 18 months, same price. While the rest of them are in the lab looking for the miracle breakthrough, and I do hope they find it, these Chinese guys are getting incrementally better. You're going to need to learn to speak Mandarin, or we have to make some changes here in the U.S. Anyway, my name's Jack Rickard. This is EVTV. We'll see you next week.